Hello, Jai Hind everyone. Today I am going to talk about the Fourier series, which is the second unit of basic signal and system. So in Fourier series, I'll talk about the representation of Fourier series, what are the Fourier series coefficient and how we can determine the coefficients of Fourier series. Then what is the magnitude and phase spectra in the Fourier series. Then among the properties of the Fourier series, I will discuss the Parseval theorem, which is very important from examination point of view and generally asked in the question as a question in the examination. And at last I will discuss one or two examples on the Fourier series. Okay, basically see there are two topics we have, that is Fourier series one and the second one is the Fourier transform. So the difference between the two topics is that Fourier series is used for the continuous time signals, which are periodic, right? And the Fourier transform is used for the those signals which are continuous time but are non-periodic signal. Okay, so as I have told you about the Fourier series representation, we know that a signal is periodic, a continuous time signal is periodic only when xt is equals to xt plus capital T, where this capital T is the time period of the signal, right? So the fundamental time period is capital C, and you can say that the fundamental frequency can be represented by 2 pi by T, right? Okay, so this is the fundamental period and frequency, and this is the fundamental time period. So we know that basically there are two periodic signals. One is sinusoidal signal, right? It can be xt can be represented by cos omega naught t or sin omega naught t. It is in the form of trigonometry. And another one is the exponential periodic signal. You can say e raised to the power j omega naught t. Here the omega naught is the fundamental frequency. So a linear combination of harmonic related complex exponential can be expressed in the form of xt, which is equals to summation k, which is equals to k from minus infinity to infinity ak e raised to the power jk omega naught t, or I can also write it as k is equals to minus infinity to infinity ak e raised to the power jk 2 pi by t into t. Okay, so here this k, it is 0. The term for k is equals to 0 will be a constant term, right? And the term for k is equals to plus minus k1 or k is equals to plus minus k term 2, this is just on, let's say k is equals to plus minus k nth. So this is the term which is having k, terms which are having k is equals to plus minus k1 are having the fundamental frequency equals to omega naught and also called as the first harmonic component of the signal, right? Similarly, harmonic component. Similarly, the term for k is equals to plus minus k2 can be referred as the second harmonic component, right? And it is having the frequency, fundamental frequency as half of the waveform, right? And similarly, k is equals to plus minus k n can be called as the nth harmonic component of the signal, right? So the representation of the periodic signal in this form is known as the Fourier series representation. Okay, now with this Fourier series there are Fourier series coefficients. So Fourier series coefficients could be of in two terms. One is the complex exponential function, another one in terms of trigonometric function. So for the complex exponential function, it can be written as a xt will be equals to over the period t, and this is from k is equals to 0 to t. Oh, I'm sorry. Sorry. xt will be equals to 1 by t over the period t, and this is ak e raised to the power jk omega naught t minus, okay, into dt. Okay, here ak is the term for k is equals to 0, a naught can be represented 1 by t over the period t, okay, into xt into dt, right? For k is equals to 0, I am talking only for k is equals to 0, right? So this is known as the DC constant, DC or constant term for the period for the signal xt. And in terms of trigonometry, if we talk about the trigonometric signals, then the signal xt can be represented as a naught, which is the same as the above equation, and here the k is equals to 1 to infinity, right? And you can say the two coefficient of the trigonometry ak cos k omega naught t plus bk sin k omega naught t, right? And the value of the coefficients ak will be equals to 2 by t over the period t, right, xt cos k omega naught t, and similarly bk will be equals to 2 by t over the period t xt sin k omega naught t, where omega naught is the fundamental frequency here, right? And the value of a naught will be same as this value, 1 by t over the period t xt into dt, okay, which is the constant term. Okay, so these ak and bk are the trigonometric coefficients of the Fourier series. So if we talk about the symmetry in terms of Fourier series, there is one concept of the symmetry in the Fourier series. See, for the symmetry means that the two coefficient, if a signal is even, or let me a naught, ak and bk. So if a signal is even, then the coefficient bk will be equals to 0 for even signal. But if the signal is odd, so the coefficient of a naught or ak will come out to be 0 when you go for the when you solve the terms a naught and the ak, the coefficients, it will come out to be 0 if the signal is odd, right? If signal is even, so the coefficient bk will come out to be 0. Now how we can we come to know whether the signal is even or odd. So to determine the signal is even or odd, we have for even signal xt will be equals to x of minus t. This is for the even signal. So for the even signal, you can say that the signal is symmetrical about the vertical axis, or you can say about the origin, right? And for odd signal, the xt will be equals to minus of x of minus t. That means the signal is anti-symmetrical about the origin. Okay, for odd signal, these two come out to be the two coefficient a naught and ak come out to be 0, and for the even signal bk will come out to be 0. So now what is the magnitude and phase spectra in terms of the Fourier series? So if we let the Fourier series coefficient ak can be written as this in terms of like this. Let's say this is e raised to power j theta. Okay. Here this mode of ak will be referred to as magnitude of the coefficient, and e raised to the power j theta will be referred to as, this theta particularly referred to as the phase. Okay? And the plot of magnitude versus omega, that is the fundamental frequency, will be known as the magnitude spectrum, and the plot of the angle, that is the angle of ak, which is equals to theta, versus omega naught, that is frequency, will be known as the phase spectrum. And together these combined will be called as the magnitude and the phase spectra. So for magnitude spectra, right, for magnitude spectra, the odd component of the it is magnitude spectra, the signal is said to be the odd component, and for the phase spectra the signal is said to be the the even components of the signals are to be taken, right. Now we have to find out the trigonometric Fourier series for the triangular periodic waveform given to us in the figure below. So first of all we have to find out the function ft, then we will go for the Fourier series coefficient, we'll find out the coefficients of the Fourier series, and then finally we'll find the value of the function ft here, right, in terms of Fourier series. So first of all you can see this is the ramp signal if we talk about, and here it is starting, if we talk about it will start from -1/2, so it will be end at 3/2, and after that the waveform repeated, right. So in this case the time period of the waveform will be equals to 2. Now I'll create the signal ft, the function ft, and whose value will be equals to, see, from -half to +half, t when t lies between -1/2 to 1/2, right, and from 1/2 to 3/2. Okay, so from 1/2 to the slope will be coming out to be, the m1 will be equals to y2 minus y1 upon x2 minus x1, which will be equals to twice of a. So here the slope will be 2a, and then this is t, the function will be this, right, and in case of from 1/2 to 3/2 the slope will come out to be -2a, and this will be t minus k1. So this is the function for this given waveform, right, and now we will solve for the we'll find out the coefficients of the trigonometric coefficient, that is a0, ak and bk. So the value of a0 will be 1 upon t, which is equals to 2 here over the period t, right, that means the time period is, let's take it over the period t, right, you can write it over the period t, that means -1/2 to 3/2, right, and the value of signal ft into dt, right, and here if we take it and split it from -1/2 to 1/2, this function, and the value is 2a into t into dt, plus from 1/2 to 3/2, and the value is, let's say, let me write it 2a t minus k, minus twice of a t minus 1 into dt. So when I solve this value, right, so the value of, you can see here, it is when I am writing it as 2a, and it will be t square by 2, let me have 1/2 at the end, and the value will be from -1/2 to 1/2, and let me take this minus sign 2 common and 2a again here, and the integration of this will be, again, this is it will be t square by 2 and minus t, and from 1/2 to 3/2, then finally I'll got the value after solving of a0 will come out to be 0. Okay, when I put these values 1/2 and minus 1/2, then I'll get the values of this finally as 0. Since you can even see this, that this waveform is antisymmetrical, so this is an odd function, so a0 and ak will come out to be 0 in this case. Now what will be the value of ak? Ak will be equals to 2/t, t is again here time period, and the function that is over the time period t from minus t by 1 by 2 to 3 by 2, okay, and this is function ft into dt. Now I'll split it, 2 will get cancelled out, right? So I'll split it from minus 1 by 2 to 1 by 2, and the function is 2a into t, 2a t dt plus 1 by 2, say 3 by 2, and it is minus 2a t minus 1 into dt, okay. So this is my value, and when I am solving it, again this will again when I'll solve will come out to be 0, as it is an odd function, right? Now odd function ke liye the values are equals to 0, trigonometric values a0 and ak. Now solving for bk, because definitely there will be a value for the bk, so 2 by t which is equals to 2 by 2, and I am directly writing these values, minus 1 by 2 to 1 by 2, and this bk, the value of bk here, see, okay, so here I have to write as well as cos omega naught t, right? And again here cos omega naught t. So omega naught, what is the value of omega naught here? See, omega naught will be equals to 2 pi by t, which is coming out to be pi, okay. So here 2 pi cos pi t, and again here cos pi t, okay. For bk it will be 2a, because here the function is ft into cos omega naught t and k, okay, and here also we'll write k, see, I'll write cos k pi t, okay, and similarly here I'll write ft into sin omega naught, sin k omega naught t, ठीक है, तो sin k and omega naught की value है pi into t into dt, right, plus another value will be from 1 by 2 to 3 by 2, and let me take this minus sign outside and I'll write it as minus 2a, which is a constant term again, and I can also write it as outside of the integration t minus k1, and sin k, this is pi t dt. Now I'll use the isolate, okay, I'll cancel out this 2 by 2, I'll use the isolate. Isolate means this is a constant term, right? ILA, okay, this is first and this is a second here, okay. So when I am solving this, so let me take out 2a as a common term outside of the integration, okay, from both the side, and this is sin t, integration of sin t into integration t into sin k pi t dt, right? So first function as it is, second ka integration, that is sin k pi t, okay, and then minus of integration of differentiation of first function, the formula is into integration of second function into dt will be the formula for the isolate, okay. And similarly here, and the values are from minus 1 by 2 to 1 by 2. Similarly here I'm taking out the value 2a, right, and I am solving for the t into sin k pi t. So I am again using here first and second. So first function as it is, integration of sin k pi t here minus overall integration and differentiation of first function into directly I can cancel, no, because of the limits I cannot cancel out, and the integration again t into dt, right, from 1 by 2 to 3 by 2, and the term minus 1 here left, right. For this minus minus plus, that is plus 2a into integration of sin k pi t, and from limits 1 by 2 to 3 by 2, right. So this is the third term, and this is the total value of the bk. While solving out this value, I'll be getting the value of bk as bk will come out to be, after solving it, that will be coming out 8a upon k square into pi square into sine k pi by 2. For k, see, this is the value. I know that for the odd terms, for k is equals to 1, 3, 5, the term will be equals to 0, and for k is equals to, let me, 8a upon k square into pi square. If I put k is equals to let's say odd 1, then sine 90 is this is 1. Let me sine 90, k is equals to 0 means sine 0 is 0, right? For k is equals to 0, term is coming out to be 0, right? For k is equals to 1, sine 90 is 1, then it is coming out to be plus, right? So I can write it at 1, यानी फिर 5 पे आएगा, 5 7 छोड़ दीजिए 9. For these odd terms I am getting the value of this. If I am getting I am putting it the value of k as 2, right? So for even terms it is coming out to be 0. So this is sine pi. So sine pi will be, हमारा sine pi हो गया, this is cos 90 which is coming out to be 0. ठीक, तो for even terms 0 to 4 the term will be equals to 0. For odd terms like 1, 5, 9, value will be 8a upon k square, and for 8a upon k square minus 8a upon k square pi square, for k is equals to 3, 7 and then 11 up to so on. So this will be the final value of the coefficient bk. Now I have to find out the function value, that is the function ft. So ft will come out to be, see, ft will be equals to a naught is 0 plus ak is 0. Then I'll put the value of the coefficient k, and finally ft, let me write out the final value of the ft, which is coming out to be, now the value was trigonometric value for summation of k from 1 to infinity, right? So for when I am putting the value of k equals to 1 to infinity, so that was the, when I am putting k is equals to 1, then it is coming out to be 8a upon k square into pi square into cos, the term was sine, and k was what was this, sine k which is equals to 1, and that was sine k omega naught t, right? See, we have done here, I have written here the values. See, this value is 0, this value is 0. Now I am putting only the values of k in this term, so that I am getting the value of the function xt, right? So here this will be sine pi t, then another, when I am putting the value of k is equals to 3, then it is minus 8a upon, oh sorry, for k here equals to 1, so it is upon 8a upon pi square into sine pi t, then 8a upon minus 8a upon, when I am putting 3, then it is coming out to be 9 pi square and sine 3t, 3 pi t, then plus again 8a upon, for value k is equals to 5, 25 pi square into sine 5t, similarly minus of 8a upon, for k is equal to 7, that means 49 pi square into sine 7 pi t, and plus up to so on. So this will be the value of the function ft here, final value of the function ft. So in this way we can solve the trigonometric Fourier series given to us, and by finding out the coefficient of the Fourier series. Now talking for the Parseval theorem, which is one of the important property of the Fourier series. So Parseval theorem says if xt is the periodic signal, right, with the Fourier coefficient as xk, then according to the Parseval theorem, the power signal will be equals to the average of summation from k is equals to minus infinity to infinity xk ka whole square, right? Let me show you the proof how it is coming. Okay, Okay, so as we know that the definition of the power is limit t tends to infinity 1 by t, right, from minus t by 2 to t by t, and the signal xt whole square into dt. This is by definition. And for periodic signal, the power signal, this is the average power. Okay, the power signal is given by 1 by t from minus t by 2 to t by t mod of xt ka whole square into dt, right? So this can be written as 1 by t minus t by 2 to t by 2, and this can be written as xt into xt ka star, that means the complex conjugate of this xt, like this, right? And we know the value of xt is equals to summation of k is equals to minus infinity to infinity, and this is xk into e raised to the power j k omega naught into t, right? And so for complex conjugate of xt star can be written as summation of k is equals to minus infinity to infinity x star k e raised to power minus j k omega naught into t. Now putting the value of the complex conjugate of x star t in this equation, that is power equation, p is equals to then 1 by t integration from minus t by 2 to t by 2 xt as it is, and the value of x star will be summation from k is equals to minus infinity to infinity, and x complex conjugate of this x k into e raised to the power minus j k omega naught t into dt for the integration. Now since taking this xk star outside, right, and with the summation p is equals to, let me take out this summation and this two terms out of the integration, because integration in terms of time hai, so there is nothing to do with these two terms xk star, right? And I can now write 1 by t outside already from the integration, and it is from minus t by 2 to t to xt e raised to the power minus j k omega naught t into dt, right? And the value of this is actually, you can see this minus t by 2 to 2 by 2 can be said as the one period, right? Signal over the one period, right? So this value can be written as xk. So here this comes out to be minus infinity to infinity. Already we have xk of star, and this value is the value of the coefficient, Fourier series coefficient xk, like this. So from here I can conclude that the power is equals to summation of k is equals to minus infinity to infinity, and I can write it as xk ka whole square, right? You can say that these two as xk ka whole square. So according to Parseval theorem, the average power of the signal will be the minus infinity to infinity xk ka mod of xk square. That's all for today's lecture. Thank you.